think we're live according to OBS. Right, okay, I think we're all good. Anyway, so well, we'll see at the end if this is recording anything or not. So this is supposed to be like a continuation of what I did on Sunday when I did a lot of hydrostatics related questions, and now I wanted a bit of variety, so I was gonna start with a bit of hydrostatics because on Sunday I have been looking at things related to that horizontal line method. So I think one of the questions that I covered on Sunday was, I think, this one. Yeah, so this is the typical kind of question that we did on Sunday, and all of them were solved in pretty much the same way. Now, I wanted a bit of variety, and one of the things that I realized I haven't actually done on, during the previous stream is I didn't look at buoyancy at all. So I think this is a good time to actually do that. So what I'm gonna do is I'm gonna start off with a hydrostatics question, and then we're gonna move on to things involving flow rates and hydrodynamics and so on and so forth. So anyway, let's have a look at something to warm up first. There was a question that I saw here, but I think, is this? Yeah, okay. I think I found it. Yeah, there we go. So that's the question. Well, I'm gonna remove this one because we're not doing it. We've already done it. So this question is like all the previous questions from the book called Fluid Mechanics. So Fluid Mechanics by Frank White. Honestly, it's one of the best books of fluid mechanics I came across so far, especially in terms of the number and variety of examples that it gives you. So yeah. One second, I'm getting a warning from YouTube. What's the problem? Okay, 1 second. I think everything should be fine. Or maybe not. Okay, there's some glitch happening. What's the problem here? Okay, well, that's sorted, hopefully. Anyway, so not sure what that was about. Anyway, so let's try to go over this question and let's see what we can do about it and how we can approach it. So pretty straightforward stuff. It says that the can in this figure is floating in the position shown in 2.104, so in the diagram that we see here. And the question is, what's the weight in newtons, right? So the only thing we know is related to the diameter of the can. So we know this is a cylindrical can. And we also know that the height is 11 centimeters. So we know that this is 11 centimeters and 3 centimeters of it is above the surface of the water. Okay, so based on this, we're going to try and figure out how to actually find the weight of the can. So what I recommend in this case to do is just draw a free body diagram. So I'm going to redraw the can here like this. Okay, and then I'm going to put all the forces that are acting on the can, right? So we have, in this case, the relevant forces are the ones in the vertical direction. So we have, on one hand, we have weight. So there's weight acting down like this. Okay, so this is my mg. And the other thing is the force due to the pressure, right? So the force due to the pressure, so I'm gonna write it here. So the pressure force in quotation marks. So the pressure force, you can think about it in two ways. So you can either find this, so you can either use hydrostatic pressure, which is the pressure acting at the bottom of the can. So essentially there is a pressure field here which is pushing the can upwards like this, and the pressure is uniform essentially. So you've got a uniform pressure distribution at the bottom of the can, which is, you know, pushing the can upwards. Or you can do this using, so you can use Archimedes principle. So Archimedes principle, which is derived from the hydrostatic pressure idea. So the way in which I'm going to do it is I'm going to look at the pressure distribution. So what the pressure does is that it creates an upward force. So this is, I'm just going to call it F or FP, right? And we know that because those are the only two forces which are acting, they must be equal to each other because this is in equilibrium. So we've got mg and Fp being equal to each other in this way. And now we just have to figure out, you know, the things that we know. So this problem is asking us about the weight. So the weight is essentially the left-hand side of this equality, which we don't know how much that is yet. But we can say that weight is equal to, and now my Fp, this is the force due to the pressure that is acting at the bottom of the can, right? So that's going to be based on the pressure multiplied by the area. Yeah, so mg is going to be equal to the pressure. So the pressure at the bottom of the can is essentially given. So the pressure is given by rho g h. And we know what the density is, right? So it's water. So we can say that the density of the water is 1,000 kilograms per meter cubed, like this. And we also know what the area is. So the pressure is therefore going to be equal to rho gh. Okay, and the area is the area of the circle. So you've got this sort of shape. So if you look into the cylinder, you're going to see this, where this is the diameter and the area is either equal to pi r squared, or if you use the diameter, it's going to be pi over 4 d squared, right? So it's going to be pi over 4 times d squared. Okay, and I think that's pretty much it in terms of, you know, things that we need to use. So all we have to do now really is just calculate the right hand side. Okay, so the right hand side, which is this, or actually let me take the whole thing with me, and this is equal to, so I have 1,000, that's the density, and then I have 9.81. Then I have the h. So the small h is this 8 centimeters because that's how far the can is submerged, right? So that's going to be 0.08 because we're using meters. And then we have pi over 4. And then this is the diameter squared, which we know the diameter is 9 centimeters, which we also convert into meters, so it's 0.09 squared. And that's it. So now it's just some number crunching and we should get the final answer. Let me turn on the light. So let's see how much we get out of this. So we have 1000 times 9.81 times 0.08 times pi, and then this is divided by 4, and then times 0.09 squared. Okay, so I get pretty much 5 newtons. So I get mg is equal to 5 newtons, and that's the answer. So if you want, you can now figure out what the mass is, right, by dividing by g, and then you're pretty much sorted out. So that's the final answer for this question. Okay, let's move on. Let's see what else we can have a look at. There's a variety of interesting hydrostatics questions where essentially we have certain dams which are acted upon by a body of water, and some dams have a curved shape, and this might be interesting. I'm not sure if I want to do that now, or I'll probably leave it for a future stream. Yeah, so I think for now I want to move on to some hydrodynamics related stuff. Okay, and just for some variety, and then maybe later or in another stream I'll come back to some more hydrostatics to do some more advanced things. But for now, what I would like to do is actually related to some mass conservation and momentum conservation as well. Yeah, so let's have a look at, again, something that's straightforward for now. So I think what I have here is a very simple and standard mass conservation problem, which is this. Okay, so in this question we are looking at an open tank, and there are a few inputs and outputs, or inflows and outflows, right? So you've got water going in through point 1, you've got water going in through 3, and then 2 is acting as the only place where the water is leaving the system. Right, and what we know is that we can assume that the water is 20 degrees Celsius and is being filled through section 1 and section 3 as well. So what we have to do is first derive an analytic expression for the water level change dH by dt in terms of volume flows Q1, Q2, Q3. So in other words, for the time being, we are assuming that we don't know how much water goes in. So we're going to say that for the time being, Q1, Q2, and Q3 are going to be arbitrary. So what we want is we want dH by dt as a function of those volumetric flow rates, Q1, Q2, Q3. So we want to see how this dH by dt depends on the 3 volumetric flow rates that interact with the system in some way. And we also have to base this on things like the diameters of the pipes, the diameter of the tank as well, and I think that's pretty much it, really. Okay, so let's try to understand what dH by dt actually is. So clearly h is the height of the water level in the tank. So h is the, I'm going to call it the depth of water in the tank, and therefore dH by dt is the rate of change. So this is the rate of change of h, and of h. So rate of change is the same as the first derivative, right? So the first derivative of h, because h is a distance, dh by dt is referring to the speed at which the water level is increasing, pretty much. So without any loss of generality, I'm gonna assume that the level in the tank, so the level in the tank is increasing with time. So when I say that, I'm basically referring to the fact that there are, or how should I say this? I'm referring to the fact that the tank itself is acting like an outflow. So the tank with the diameter lowercase d acts as an outflow. Okay, so in this case, what I'm gonna say is that I have two inflows and two outflows. So this is in, this is also in, this one is out, and the water in the tank increases, so this acts as an out as well. So this one is going up too, so this is also out. So I have two going in and two going out. So in this respect, I can then use mass conservation. Yeah, so I can say that mass flow rate going in is equal to mass flow rate coming out. But because of incompressibility effects, so I know that the density is constant. So because the density is constant, this is equivalent to saying that the volumetric flow rate in is equal to the volumetric flow rate out. So I can then write the formula for the volumetric flow rates going in and out. So what goes in is at 1 and 3, right? So I can say that, let's change the color. So Q1 plus Q3. So this is, in for both of them. And then I have the volumetric flow rate going out, which is at 2. So this is equal to Q2 plus. Now we also have this water level in the tank increasing. So let's think, what is the volumetric flow rate of the tank? Well, we know that the velocity, let's use U for this. So I know the velocity of the water in the tank is given by dH by dt. That's the rate of change of height. I know the area, so the area is based on this diameter here, so the area is going to be pi over 4d squared, because it's a it's a cylindrical base, a cylindrical cross section. So this is going to be equal to dH by dt multiplied by pi over 4d squared. Keep in mind, this d and this d are not the same. Yeah, this is an actual variable. This is just a notation that's part of the derivative expression. Anyway, so what I'll do now is I'm going to rearrange this to get an expression of dH by dt. Okay, so I'm going to say dH by dt times pi over 4d squared is equal to Q1 plus Q3 minus Q2. So dH by dt is equal to Q1 plus Q3 minus Q2 over pi over 4d squared. Or if I want to get rid of all those fractions stacked on top of each other, I can just call this 4. Yeah, let's do it like this. So 4 Q1 plus Q3 minus Q2 divided by pi d squared. Okay, So I think that should be the answer for part, well, there's no part A and B, it's just for the first part of the question. Anyway, so what we have to do in the next part, so the first part was until this point, and now it says that if the water level H is constant, determine the exit velocity V2 for the given data. So we know the inlet velocity at 1 is 3 meters per second. We know this volumetric flow rate is 0.01 meters cubed per second. So let's try to figure out what V2 is by using what we have here. Okay, so what I'm gonna do is I'm gonna say that I'm gonna call this part A, and now I'm gonna move on to part B. So I have an expression for the rate of change of the height, which is 4, and then I have Q1 plus Q3 minus Q2, and this is divided by pi d squared. So in part B, we know that H has to be constant. We don't know how much it is, but we don't really care how much it is, because if it's constant, it means that dH by dt is actually equal to 0. Yeah, there's no rate of change of height. So we can then take this and equate it to 0 as well. So we've got 4 and then Q1 plus Q3 minus Q2 over pi d squared is equal to 0. So if this fraction is equal to 0, it means the numerator is equal to 0. So we've got Q1 plus Q3 minus Q2 is equal to 0. Right, now let's remember what we have to find. So we have to find the velocity at, the velocity here, which, yeah, we don't know this. We know this as 3 meters per second, and we also know this volumetric flow rate, which is given as well. So all we have to do now is just manipulate this around, and we'll get the answer quite easily. So we have Q1 plus Q3 is equal to Q2. So Q1, we don't know Q1, but we can kind of, derive an expression for it quite easily. So this is V1, and then I have pi over 4, I think it's capital D1 squared, like this, plus Q3 equals, and then with Q2 we do the same thing, right? We express it in terms of V2 and the diameter. So we've got V2, and then we have pi over 4 D2 squared. Okay, and remember that what we need to find is V2 in this case. So if I divide everything, or if I multiply by 4 over pi 1 over D2 squared, then what I'll get on the left, or what the equation will become actually, is going to be V2, and then this is going to be equal to everything on the right divided by the thing that I wrote there. So we have this plus Q3 divided by pi over 4 D2 squared. Okay, I think that's it. So therefore V2 is equal to V1, and then we can split the fraction. So this is going to be D1 over D2 squared plus, and now we have Q3 over that, so this is just 4, so 4Q3 divided by pi D2 squared. So this is the final expression for the velocity, right? So therefore from here we can plug the numbers in. So V2 is going to be equal to V1. So V1 was 3 meters per second. D1 and D2, so this is 5, this is 7, so it's 5 over 7 squared. The units don't actually matter in this case, so whether I use meters or centimeters, it's irrelevant, because they, I divide one by the other essentially. plus, so this is going to be 4Q3, and Q3 is 0.01, and then D2 is 7 centimeters. So now I'm gonna convert to the right units. So that's 0.07, because that's what D2 is, squared. Okay, so now we just put the numbers in, and we're gonna get something which is, let's see, so 5/7 squared times 3. Okay, so the first term is 1.53 plus, and then the other one is 0.04 divided by pi, and then divided by 0.07, and then divided by 0.07. So this is plus roughly 2.6, which is equal to, so it's 2.6 plus 1.53, so roughly 4.13 meters per second. And that's it. So that's the answer to the question. So imagine that you basically have a valve here, right? So imagine this is a valve. So you can reinterpret, you can rethink about this question in terms of how much do I have to open the valve so that the level in the tank stays the same, right? So if you have a way to measure the speed of the flow, then using this configuration and assuming, of course, inviscid flow, then the velocity of the fluid at the outflow should be set to 4.30 meters per second. So in this case, or in that case, the height in the tank is going to stay constant. If you start closing the valve, so if V2 starts going down, right? So if you decrease V2, then dH by D2, dH by dt is going to start increasing. If V2 increases, then the level in the tank starts going down. So actually, there's probably a better way for me to write this, and I know what that is. So if V2 is less than 4.13 meters per second, then if you think about it, the dH by dt is going to be positive, right? Which means that the height in the tank is going to increase. And if V2 is bigger than 4.13, so let's say if you fully open the valve, then the level of the water in the tank is going to start dropping. So that corresponds to the height decreasing over time. And the only time where you have equality, so if V2 is precisely equal to 4.13 liters per second, then dH by dt is identically 0, which corresponds to the h being constant. So there we go. That's the question, and this is part of trying to understand the question a bit better. Okay, so that's sorted. Let's move on to something else. So I have here something that's a bit more involved mathematically, which is still just based on mass conservation. So I'm looking at this question. So it may not seem like much, but the fact that it has a star, right, it's an indication that it's a bit more involved, and I think it is a bit more involved if you consider the maths behind it. So let's try to read it, let's try to understand it, and then we'll attempt solving it. So this one says, water enters the bottom of the cone. Okay, now I wouldn't really call this a cone. This is more like a funnel shape, right? So this is more like a funnel shape. more than anything. But as you'll see, we can actually almost treat it as a cone because of some of the assumptions that are at play. So anyway, we know that water enters the bottom of the cone with this velocity, right? So we're pumping in water at a rate. So I can almost say that this is a function. I mean, I can not almost, I can definitely say this is a function. So I know that the velocity with respect to time is equal to kt. So we obviously start measuring time from 0. Yeah. So what this says is that the velocity essentially increases with time, because I'm gonna treat, I mean, the question doesn't say this. No, it does say it specifically. It says that it's increasing average velocity. So v is increasing with time. So v is increasing, which implies that k is a positive constant. Okay, so if you try to plot this out with respect to time, so let's say this is the velocity and then this is time. If you plot this out, you're gonna get something that starts from 0 and then it increases in this way. So this is my function v, which is equal to kt, pretty much. So we pump water in this strange looking system at this with this speed, with this velocity, and we know that the water goes in through a circular orifice which has a diameter. Okay, but we're told that d is very small, so this is definitely gonna be useful. So I'm gonna say d is very small. I'm putting it in quotation marks because this is not really a very technical term. So I'm gonna say that d is much smaller than, so d is much smaller than h. And this is gonna be something that's gonna be useful in a bit, and we'll see why that's gonna be the case. So what we have to do is we have to derive an analytical formula for the water surface rise ht. So yeah, we have to basically say what is ht equal to. So what I want to know is at any given time, not just at the initial time of 0 seconds, because I know what the answer is going to be in that case. I'm being told that at t equals 0, the height is 0. So in other words, at t equals 0, the water level is like this. Or actually, that's not entirely correct. It's actually like this. So this is t equals 0. Okay. Right. And then we assume incompressible flow. Yeah. So that makes things easier. So we know the density is constant. And we know we're talking about water, so that's just 1,000 kilograms per meter cubed. Okay, so this is clearly mass conservation at play, because if you think about it, this is just one inflow and one outflow, right? So this is, or you can call it inlet and outlet or whatever. So this here, this is my inlet, and this is my outlet, right? So, and I must have mass constant, so the mass flux or the mass flow rate has to be constant, which is the same as saying that mass flow rate in is equal to mass flow rate out. Okay, so this is going to be my starting point for all this stuff. So let's try to maybe write some things down that we know. So the mass flow rate in, this is going to be based on the inlet, obviously, right? And the mass in is going to be equal to rho AV. That's the general formula. So in this case, it's equal to density. We know that the inlet has a diameter, so it's actually a circular cross-section. So this is pi over 4d squared. And the velocity is kt. So the velocity is kt, like this. So clearly the mass flow rate in increases with time, right? Because it's based on velocity, and velocity increases with time. So clearly the mass flow rate also increases with time. Now the other thing I'll have to do is find an expression for the mass flow rate out, right? So I'm gonna have m dot out equal to, so if you think about, you know, what's happening here is that this free surface is increasing, well, I should say it's going up, but as it's going up, the surface area is increasing as well, because let me get rid of this here. So when the height is here, you know, this corresponds to, let's say, this cross-sectional area, but when the surface is here, maybe this corresponds to this cross-sectional area. So the cross-sectional area is clearly changing, and more specifically it's increasing with time. So, you know, we're gonna have to find a way to take that into account. So what I'm gonna do in that case is I'm gonna, first of all, I need this diagram again, so I'm gonna copy it onto this page. And then I'm gonna say that this is the radius of the base of this cone, right? And this is gonna be the radius as a function of time, because we know this also changes as a function of time. Right. Now, the other thing I'll say is that this inlet pipe here, I'm gonna say it's very small. And I don't actually like the fact that they measure h from the bottom. I think it would make more sense, actually, to measure the h from here, because I don't really care what happens below that kind of, you know, fake vertex of the cone. So whether you measure h from here or from here, it doesn't really change anything, because what I want to know is what happens within the conical shape itself as the water goes up, right? So what I'm gonna do then is I'm gonna change this slightly, and I'm gonna say that h is actually measured like this. It's gonna be more convenient for the analysis, because this part is basically irrelevant. It doesn't do anything. Okay, so let's try to figure out what we have to do in this case. So the m out, the mass flow rate out, that's based on the density. It's based on the area of the, you know, on this area kind of, which is given by the radius. So this is going to be pi r t squared. That's the, you know, area, and then multiplied by the velocity. So this is going to be the velocity of the free surface going up. We don't know how much that is. We would like to know how much that is, but we know that the height is given as ht, right? So if the height is given as ht, then we can write that velocity as just the rate dh by dt, like this, because that's what the, you know, the velocity of the free surface is. So as the velocity of the free surface is pointing upwards, so this is the velocity of the free surface, and this is the rate of change of height. Okay, so what I'll do now is I can use mass conservation, so I can make the two equal to each other. So we have rho, and then I have pi over 4 d squared kt, and this is equal to rho, and then I have pi r squared. I'm gonna drop the brackets t because that's obvious, and then I have dh by dt. Okay, so I have one independent variable, which is time, and I have two dependent variables, which I don't really like. So I have r as one thing, and I have h, which is the other thing. And ideally, I would like to express everything in terms of either r or h, and we can do that. And I want to express everything in terms of h because the question is asking about h, right? Now, the way I would do this is I would, first of all, I would use the fact that d is very small. So if I take that into account, here's what we have. So if I make a drawing of a right triangle like this, let's try to make it, okay, that should be good enough. So this side, this is my r, okay, this is my h, and then I have that angle of the cone which is here, so I have that angle theta, which is, that's not changing, that's not a variable, right? That's just whatever the opening of the cone is, and that cone is made of a solid material, so nothing actually changes in that regard. So what I can say is that tan theta is equal to r over h. So that's r over h, like this. Yeah, that's fine. And then I can express r in terms of h tan theta. Okay, so this makes our life a bit easier because when we plug this back in, we don't actually have to worry about having two variables. We just have h and of course t. So let's do that. So I have rho, and then I have pi over 4. I have d squared, and I have kt. And then I have rho, and I have pi. Now instead of r squared, I'm gonna write this as h squared tan squared of theta, and then dh by dt. So dh by dt. Okay, cool. I think that's making sense now. So we have one function basically, which is h, which appears on one side of the equation. So what we want out of this is we want to find what is what is h basically. That's the goal. So thankfully this tan of theta is constant because theta is constant, so we don't have to worry about dealing with that when we integrate it. So let's cancel out a couple of things. So the densities cancel out, and I think the pi cancels out as well, like this. So on the left I have d squared kt divided by 4, and then on the right I have h squared, and then I have tan squared theta dh by dt. So what we're gonna try to do is we will attempt to find h, and to do that we'll have to integrate, and it's not a difficult integral at all. All we have to do is just rearrange this a bit to and separate the variables pretty much. Okay, so this is going to equal, let's see, so I want all my h's on one side, so I can write this as h squared dh, which is, you know, this and this. So I'm gonna keep this on one side, and then I'm gonna put everything on the other side. So that's d squared kt over 4, and this is going to be dt over tan squared of theta. Yeah, just double checking the math. I think everything should be fine in this case. So dt over, yeah. And now we integrate. So we integrate both sides. And the first, the integral on the left is going to be h cubed over 3. Right? And on the right, I actually have a lot of constants that I can just take out. So I have d squared, I have k, I have the 4, and then I have tan squared theta, and then I have integral of t dt, like this. So when we integrate when we fully integrate the right hand side, that's going to be, so k d squared over 4 tan squared of theta, t squared over 2 plus constant. Yeah, so I have my constant of integration, which this is not difficult to figure out that it's actually equal to 0, right? So I know that h of 0 is equal to 0 based on this. Yeah. So at t equals 0, h is equal to 0. So if I plug those in, I have that 0 is equal to 0 plus c. So my constant is identically 0. So now if I rearrange, I should get that h cubed over 3 is equal to just this. So I have k d squared t squared over 8 tan squared theta. Okay. So we have h cubed. Now I just want to get h by itself, right? So this is going to be 3 over 8 k d squared over tan squared of theta multiplied by t squared. And finally, if I want h by itself, all I have to do is just rewrite this whole thing like this. So tan squared theta t squared, and this is going to be raised to the power of a third, and that's it. Or, you know, if you want, you can write it like this. So 3 over 8 kd squared over tan squared theta t squared, and this is the cubic root of that expression there, and that's it. So that's pretty much the answer. And obviously we don't have any numbers, but we don't really need them. So what we have here, on the other hand, is an explicit expression of h as a function of time. So another way to write this is to consider the fact that this is a constant. So this is constant, which means that I can write it as h is proportional to time to the power 2/3. So this is how the height varies with time, pretty much. So that's essentially it. Okay, let's see how. Let's see what else we can perhaps have a look at. So for this question, we have. Yeah, so we got 3 over 8 times that thing. Okay, so that was just a relatively straightforward problem from a physical point of view, but the maths was a bit more advanced than average, I would say. Okay. Now having a look at some other questions on momentum, but I think before I get there, I think there's probably something else that I want to do on mass conservation instead. Okay, I think this one is interesting, and it's a bit unusual as well. So what I'm looking at is this. Now, to tell you the truth, the first time I've seen something like this was in cartoons. when I was a kid. I don't think I've ever seen one in real life, but I know what they're used for. I mean, I know one thing that they're used for. They used to use this in cartoons to kind of blow air into the fire to make the fire stronger. And yeah, I've never seen one of those in real life, so I assume they're not really as common anymore, but they make into a nice fluid mechanics problem at least. So anyway, let's try to read the question, and as usual, let's try to understand what everything is about. So this is called a bellows. So before reading this question, I actually didn't know what this thing is even called. So a bellows may be modeled as a deforming wedge-shaped volume. Okay, so if you look at this in 3D, I guess what you can model it as. So this is the 2D section of it. So that's kind of how it looks in 2D, but in 3D, it's kind of like this, right? So it has a depth into the paper, like that. So, this is like a very simplistic view of how this bellows looks like. So what we know is that H is kind of like the half of the base. So this distance here is given by 2H. And then we have the length, which is given by this. So this is L. And then this is theta. So this is what we know so far. And then it says the check valve on the left. So there's a valve here. And while you're performing the stroke, that valve is closed, which kind of makes sense, because if this is open, so if you imagine, if you imagine there's a hole here, when you perform the stroke, air is gonna come out on both sides, and you don't really want that, because if you have this pointed towards something like a fire, you want all the air to come out through here, and you don't want any unwanted leakage coming out from the back. That's not really what the point is. So it must have a valve which is able to close automatically when you're performing the stroke, pretty much. So yeah. Now the stroke itself is quantified in terms of that angle theta. So the stroke is basically given by this angle theta t. Okay, and we also know that B is the width into the paper. So this side here, this is what B would be like, and we have to figure out an expression for the mass flow rate. So we want to know what's this m dot 0 as a function of theta. So in a sense, it's similar to the previous question, because in the previous question we also wanted to figure out a relationship between, well, in this case it was the height and time. In this case we want to find the relationship between the mass flow rate and this angle here, theta. Okay, and this one doesn't have a star, which means the math shouldn't be as complicated. So let's see what we can do about it. To be fair, what I would do is I would probably try to find an expression for the mass of air. So here's my strategy. I'm gonna find an expression for the mass of air inside the, what's the name, bellows. Yeah, that's what I would do. And I think another assumption that we have to do is we most likely, I mean, this is not true in reality, but because, you know, the action is performed relatively slowly and the air can actually escape, we're gonna assume that the air in this case is incompressible. So yeah, so keep that in mind. We're gonna treat the air as incompressible, and what we do in that regard is just find what's the mass of air inside the shape. So to do that, I'm gonna say that the mass is equal to the density times the volume. Yeah, so that's pretty standard. The density is, I'm just gonna keep it as rho, and the volume is the volume of this whole shape, because air takes up all the available space because it's a gas. So this whole thing, this is the volume that we want to use, that we want to calculate. So that's gonna be based on two things. So it's the area of the triangle. So the area of the triangle multiplied by the B, which is the width of the bellows. Okay. So we've got rho, and then we have the area of the triangle, which is just base times height over 2. So this is 2h times L over 2. This gives us the area of the triangle. So 2h times L over 2, and then we multiply this by the width, and that's the volume. Okay, so we can cancel out the 2's, and we get rho, and then we get h, L, and B. Okay, now, like in the previous problem, we've got two variables here to play around in a way. Now, and as usual, you just want one variable. And the variable that we were told about is theta, and clearly theta is a variable, right? Because theta is changing. So as you kind of like compress that bellows, theta decreases. So this one decreases with time. And the other thing that decreases with time is h, right? So this one also goes down. On the other hand, B is constant. So I'm going to write here that B is constant, which is good. Yeah, we like things to be constant. We like finding constants in our problem. And the other thing that's constant is L. So L is also constant. Right? So L stays, L is basically the horizontal projection of a leg. I think it's called a leg. Yeah. So L is the horizontal projection of one of the legs of the bellows. Okay. So what we can do is we can do some trigonometry and say that, you know, I have a line here, I have one here and one here, and this pretty much gives me a, well, imagine this is a right triangle like this. Okay, so that right triangle, what we can say is that I'm going to say that tan theta is equal to h divided by L. So if we rearrange for h, this is just L tan theta, like this. Okay, so that's it. So the mass of, this is the mass of air, remember? That's the mass of air inside the bellows, so that's rho, and then we have h, which is L tan theta, so L tan theta, yeah, this used to be h, and then I have L again, and then I have B. So I don't worry about L and B because they're constants, so this is going to be equal to rho L squared B tan theta. So really the only variable in this is theta, because theta is basically changing with time, right? It's decreasing as the bellows is doing this. Everything else is constant. And that's good because now we have to differentiate this. The reason we have to differentiate it is because that's going to give us the rate at which the mass is changing, pretty much. So I'm gonna say that the dm air by dt is gonna be equal to d by dt of rho, and then I have L squared B tan theta, right? And this gives me the mass flow rate because there isn't any other place in this system where air is leaving, right? We only have that main exit at the tip. The valve is closed, so we have one inlet. Well, actually we don't have any inlets, we just have one outlet, right? So we have air trapped, and then it's leaving the system, and it happens at this rate. So the rho L squared becomes outside, and now we have to differentiate with respect to time tan of theta, and theta itself is a function of time, so we're gonna have to apply the chain rule in this case. So m dot is equal to rho L squared B, and now the time derivative of tan is 1 over cosine squared of theta, and according to the chain rule now we have to differentiate theta as well, and we have this. So finally we can say that the m dot air equals rho L squared B divided by cosine squared of theta times theta dot, and that's it. Okay, so that's the mass flow rate of air as it's leaving the system, as it's leaving the bellows. And you know, if you look at what I have here, this just depends on theta, because I mean, yes, it depends on rho L and B, but they are constants. But the only variables I have is theta. So I have cosine of theta squared, and I also have the rate of change of theta, because I don't know how much that is, but clearly this must be a factor, because theta dot is a measure of how fast the bellows is being closed. So if theta dot is big in magnitude, it means I'm closing the bellows as fast as possible. So that's gonna correspond to a high mass flow rate going out. Whereas, if I do this very slowly, then theta dot is gonna be slow. So I have a small mass flow rate, pretty much. Okay, and yeah, that's basically it. Okay, so now we've done that as well. I think what I want to do now is probably just something on momentum as well. Yeah, so we've done mass, we've done a bit of hydrostatics, and there is some stuff on momentum that I want to cover. And there's a nice question here which I saw, which is covering quite a few things. So this is the first part of the question, but then it's got a few more bits and pieces here like this. So it should be like that. Right. Okay, so let's read the question and let's see how we can start going through it. So we know that in this figure, a jet strikes a vein which moves to the right at a constant velocity vc on a frictionless cart. So frictionless cart basically means that there's no friction with the ground, between the ground and the wheel. So it's free to move unrestrained. And what we have to find is find the force Fx, which is this one, required to restrain the cart. Okay, and then we have to find in part B the power P delivered to the cart. So, and then we have to do a few things in part C and D, but we'll get to that. We'll cross that bridge when we get there. So let's try to understand what's happening here. So we have a cart that's stationary, and then we fire this water jet onto it, which is, you know, it's traveling and then it's being deflected by an angle theta, like this. And then the cart starts moving, and we need a force to restrain it. So we have a force that we apply, but in the same time the velocity of the cart is constant. So the first thing that I would ask is, why do we need a force Fx? Because are we really restraining the cart if it's allowed to move? And the answer is yes, because if Fx didn't exist, think what would happen to the cart. So you have this amount of water, this amount of momentum that is traveling. I don't even know if it's water, but it just said it's a fluid, it's a jet. So if this momentum is going in and then leaving the system, it's going to exert a force on the cart. And if you don't restrain it, so if Fx didn't exist, the cart would accelerate. The cart would accelerate. And the issue with that is that if the cart accelerates, the velocity of the cart would change, right? So the velocity of the cart would change and it wouldn't be constant, but we know it's constant, therefore we must have a force to have that acceleration as zero. So this is pretty much what's happening. That's the logic behind everything. Now, other than that, what I would do to solve this is I would first draw my control volume. So I would draw something like this around the cart, and then around this part where you have the water jet leaving, and so on. Yeah, so I have one inlet here, I have one outlet, so I have, you know, 2 points where the jet leave the system or enter the system, and the other thing is I have a force that's holding this car from accelerating. It's not holding it still, but it's just keeping it from accelerating, which is Fx. Fy, I'm not really going to care about Fy because, well, first of all, the question doesn't ask about it. And yeah, that's essentially it. So we're gonna apply momentum conservation on the control volume to figure out the force Fx. So for part A, we just have to figure out what is Fx. Now the other issue that we have is that this control volume is not staying stationary, it's moving. And that's a bit annoying. We can definitely deal with it, and there's a few ways to do it. So one of the ways is to use Reynolds transport equation. So Reynolds transport equation, and that's method one. I'm not going to use this. Reynolds transport equation, or RTT, this is super versatile and it can be used to solve any similar type of fluid mechanics question where the control volume is moving, accelerating, rotating, or anything you want, basically. In this case, I'm not going to use it because it's kind of like killing ants with a shotgun. Instead, what I'll do is I'm going to change my frame of reference to the cart. So what I'll do is I'm going to imagine that I'm an observer sitting on the cart. So I'm going to say that I'm, you know, here, and I'm moving with the cart, and then I'm looking at what happens relative to the cart that's moving with that constant velocity. Okay? So if you think about it, you've got the velocity of the jet going in, but I'm also moving with the velocity vc, like this. So what I actually see as an observer is not, so if I look at the water jet coming in, I'm not actually going to see Vj, I'm going to see a smaller relative velocity, and that's the key word here, it's relative velocity. So if I look at the water jet, I'm going to see Vj minus Vc coming towards me, right? Whereas if I was to move towards the water jet, I would see the water going towards me much faster, but in this case it's going to be slower because I'm kind of moving with it. Yeah. So if we draw the shape of the jet, or if we redraw this free body diagram or this control volume with this in mind, things are going to look a bit different. So here's what we have. So let's say this is the vane, which is attached to the cart, which has some wheels and so on. So this is now my frame of reference. And I know that the width or the thickness of the jet stays constant. So I've got this thing here happening. So I have this water jet having the same diameter all the way through. So when I do my, my control volume analysis, I know that the water that goes in, it actually goes in at the velocity of Vj minus Vc, because I'm looking at it from my frame of reference, and again, I'm standing on the cart like this. So this is what I see basically. And then the water leaving is gonna have the same relative velocity Vj minus Vc, and mass has to be conserved, so it has to have the same velocity. And then I also have this force that's used to restrain the cart. So all we have to do now really is just apply the principle of momentum conservation, which is that the sum of forces specifically in the x direction are going to be equal to the momentum flow rate in x going out minus the momentum flow rate in x coming into the system, like this. So my only force is going to the left, so I'm going to write that's minus fx equals, and I think there was an angle here as well, which that's theta. Okay, so the momentum going out in the x direction, that's based on the mass flow rate, which is the same at both ends. So I'm gonna maybe write this down. So the mass flow rate at 1 is the same as the mass flow rate at 2, which is equal to just m dot. And the x velocity out, that's based on this, on trigonometry and on Vj minus Vc. So I have this, and if I care about the velocity in the x direction, that's Vj minus Vc cos theta. So that's going to be m dot, and then I believe this is just Vj minus Vc cos theta, like this. Minus, and then the momentum flow rate going in is the mass flow rate times the, times this Vj minus Vc, and that's essentially it. So if I rearrange, I get minus fx is equal to, so I can definitely factorize a couple of things like this, and then my fx is therefore m dot Vj minus Vc, and then 1 minus cos theta. So we just multiply by -1 both sides, and then I ended up with this. Let's add a few more pages. Okay, so this should be the answer for part A. So therefore, to keep this cart from not accelerating, so to keep it as an inertial frame of reference, we have to exert this force. And that's basically it. Okay, for part B we have to find the power delivered to the cart. So we have to find the power. So the power is essentially based on the force times the velocity of the cart. So pretty straightforward. So this is going to be equal to m dot, and then I have Vj minus Vc. 1 minus cosine of theta times Vc. Oh, and another thing, this m dot, we can actually express it in terms of, you know, other things that we know. So actually this Fx is equal to the density, and then we have Aj as the area, so this is rho, Aj, and then the velocity going in is Vj minus Vc. So it's Vj minus Vc twice, so it's going to be squared, and this is going to be 1 minus cos theta, like that. Okay, so what we then have is this is equal to rho Aj, and then we have Vj minus Vc squared, and then we have another Vc, 1 minus cos theta. So we have this for the power. And then for part C, we have to calculate, so find the cart velocity for which the force Fx is maximum, and then on part D we have to find Vc for which the power is maximum. So in part C we want to maximize Fx, and we know Fx is equal to rho Aj, and then we have Vj minus Vc squared times 1 minus cos theta. So if we want to maximize Fx, we have to differentiate. So we have dFx by dVc is equal to 0. So when we differentiate, we get rho Aj, and then we have 2 Vj minus Vc times, well, now we have to use the chain rule, and this is going to give us another minus 1, and then 1 minus cos theta, and this is going to be equal to 0. So in this case, if we want to maximize the force, you know, if we make this equal to 0, then what this means is that this is going to be equal to 0. Therefore, Vc is going to have to equal to Vj. So when the cart has the same velocity as the jet, that's when the power is maximum, essentially. So yeah, hopefully that makes sense. And you can, in a sense, you can try to imagine what that means. So if you, if for example you plug in the numbers, so if you have Vj as, or if you have Vc as Vj, well, that actually gives you 0, which seems a bit, I believe this seems a bit off. So what we should try to do instead, yeah, so when Vc is equal to Vj, we have a stationary point, but it doesn't guarantee that the stationary point is what we're looking for, right? Because if you think about it, the velocity of the cart has to have certain bounds. So the velocity of the cart has to be something greater than 0, unless it is moving the other way around, but we're gonna assume that it's moving to the right. So the velocity of the cart is clearly above 0, and I'm gonna argue that it should be less than or equal to Vj as well, or it could be 0 too. And the reason why it has to be less than Vj is because if the cart moves faster than the jet, then the jet never reaches the cart in the first place. So we're not going to have this problem at all in the first place. And this gives us a stationary point here, but this doesn't really help us, because if you plug in, so if you do F calculated when Vc is equal to Vj, that's going to give you a force of 0, which doesn't really make sense. So as usual, when calculating the min or the max of a function, we have to check. So we have to check the boundaries. So we have to check the boundaries manually. So the boundaries are this and this, and we know what Vj is. We know that the force at that point is 0. So let's try the other one. So if we do F at when Vc is 0, this seems a bit more appropriate. So this is going to give us rho Aj, and then we have Vj squared times 1 minus cos theta. Okay, so this actually makes sense to be the correct answer, because if you think about it, if the cart is stationary, then you have to apply a large amount of force to keep it in place. Whereas if it starts moving with some velocity, that velocity has a relieving effect, and you don't have to apply that much of a force to keep it moving to some extent. But if you want the car to be to stay in place, you have to apply the highest possible force. And of course, you're gonna apply an even higher force if you start pushing the cart against the jet as well. So hopefully that makes sense. And finally, the last part of the question, so D, is asking us what's Vc for maximum power. So we have the power, which is equal to whatever we had in part B, which is this. So this is rho Aj, and then we have Vj minus Vc squared times Vc, and then 1 minus cosine of theta. Yeah, okay. So a few things before we start going into this. Our goal is to maximize power, and clearly the same approach as before is not going to work, because if you make Vc 0 like before, then you're not delivering any power, because power involves, you know, moving things. But if you know the thing is stationary, then you're not really adding any power to it. Similarly, if Vc is equal to the velocity of the jet, the power is also 0. Yeah, so in that case, the cart and the jet are moving at the same rate, so once again you're not delivering any power. So the right answer in this case is most likely going to be somewhere in between. So the hypothesis is that for maximum power, the velocity, which you know, I'm gonna say Vc star, is gonna be somewhere between 0 and Vj, but it's not gonna be either of the two ends. And to figure this out, what we're gonna do as usual is just differentiate the power. Actually, I'm not even gonna differentiate the entire expression, because this is the only part that is gonna be relevant in this case. So if I say that dp by dvc is going to be equal to 0, then what I can do, well, first of all, let me try to expand the bracket, and I want to take this and I kind of want to put it inside the bracket. So this is going to give me Vj squared Vc, and then I have minus 2 Vj Vc squared, and then I have plus Vc cubed multiplied with that other thing, cosine of theta. So now when I differentiate this with respect to Vc, what I get is rho Aj, and then in the brackets I'm gonna have Vj squared, then I have minus 4 Vj Vc plus 3 Vc squared times 1 minus cosine of theta, and this has to be equal to 0 to find the stationary points. Okay, so I think what we do now is we just have to solve what's inside here, and we have to make this equal to 0, because if this expression has to be equal to 0, the only point where we can make it equal to 0 would be here. So yeah, hopefully that makes sense. So let's see what we get. So if I rewrite that expression, which is essentially a quadratic, then what I get is Vj squared minus 4 Vj Vc, and then I have plus 3 Vc squared is equal to 0. Okay, so let's try solving this, and the way I'm gonna do it is using the using the quadratic formula and all that stuff. So first of all, I'm gonna rewrite it in standard form. So 3 Vc squared minus 4 Vj, and then Vc plus Vj squared is equal to 0, and then my discriminant is going to be 16 Vj squared minus 12 Vj squared, which is going to give me 4, and then the Vc is going to be minus b, so I'm using minus b plus or minus square root of delta over 2a. So this is going to be 4 Vj plus or minus 2 Vj divided by 6. Okay, so we have two solutions. One of them is Vj over 3, and the other one is Vj. We know it's not this one, right? Because this one gives us a power of 0, which we don't really want. This one might actually be correct, but we have to check, and the best way to check it is to take the second derivative. So let's take this expression of power and differentiate it again. So if I differentiate it with respect to Vc one more time, this is going to give us the following. So we have rho Aj, and then we differentiate what's inside the bracket. So we have 0. Yeah, this turns into 0. Then the next bit is going to be minus 4 Vj. Yeah, that's fine. So minus 4 Vj, and then finally we have plus 6 Vc. So plus 6 Vc, and then of course my 1 minus cosine of theta. So let's try it out, and let's see if this is actually if Vc is equal to Vj over 3 is actually a maximum. So I'm going to take this, plug it in here, and I have that my second derivative with respect to Vc at this point is going to be equal to this, and then we have minus 4 Vj, and then plus 6 times Vc, which is Vj over 3, times 1 minus cos theta. And it looks like everything is fine, because this is now a negative value. So I have minus 4 Vj plus 2 Vj, so the whole thing is going to turn into minus 2 rho Ej Vj1 minus cos of theta. So this is negative, and according to, you know, the theory of calculus, if your second derivative at a point is so if x0 is less than 0 and if f prime of x0 is 0, then thank God x0 is a maximum, local maximum. Okay, so all done. We know the bounds don't work, so you know we've checked the bounds independently before, so they both give us a power of 0, but that doesn't give us anything of interest. What does correspond to the highest power is if Vc is equal to Vg over 3. So in that case, we are able to deliver the maximum amount of power to the cart, and that happens when the cart is moving with a third of the velocity of the jet. Yeah, and that's essentially it. So for the maximum power, sorry, for the maximum force, that was part C. So to maximize the force, we have to make the cart move with 0 velocity. So the cart is stationary, and that gives us maximum force. If we want maximum power, the cart has to move with a third of the velocity of the jet. And that's pretty much the end of the question. Yeah, and that's pretty much the end of the stream as well. So I see there are 3 people watching it. So if you were here all along, I hope you learned something. If you want, you can go through the stream again afterwards and try to do some of those examples yourselves. But in any case, I'll see you next time. I'm not sure when next time is going to be, but yeah, we're probably going to do another stream where we do a few more hydrostatics, some more tricky concepts, and some more, mass, flow rate, energy maybe, and some more momentum as well. So thanks for sticking with me, and I'll see you next time. Take care and have a good day.